Welcome, everybody. Today is the Engineers Australia webinar follow-up training. Welcome to our webinar training series. My name is Young Park from MIDAS IT Australia. I'm the account manager at the MIDAS IT Australia and handling ANZ regions. Here is our contents for today. First, I'll welcome and introduce our hands-on training session, what we're going to learn and what we're going to cover. And second, Harsha will take over and he'll explain and then go through with the concrete gravity dam to the modeling and analysis. And then at the end, we will wrap up with Q&A and closing sessions. So here is our instructions of today's webinar. Last Wednesday, we had a webinar with EA. The series name was Revolution of Dams and Hydropower designed by MIDAS IT. First, we covered the market of dams and hydropower. Then we will go through with the FEA NX features and modules. Then we had a speaker named Dilabo who covered the project application using FEA NX. So what we will learn today is the modeling of the concrete gravity dam in 2D, then simulation of tension crack, then we'll cover the principal stress and maximum tensile stress zones. During the webinar training session, if you have any question, there is a top menu and Q&A sector. You can click on it and the Q&A part will be shown on right corner. So you can just simply type any question, then we will try to answer you live. And if we can answer all the questions, we will follow through via email. Then if you have a question at the end of it or you want to ask us separately, you can always send the email. All right, so now Harsha will take over and he will go through our session today. And thank you everybody for joining again. And here's the Harsha. Harsha?
Hello everyone, this is Harsha. I hope you can hear my voice.
Yes, we can hear your voice.
Perfect. So thanks for attending this training webinar series. And this is a follow-up training to the Engineers Australia webinar that we have done on April 2nd. So in that, as Young explained, in that Engineers Australia webinar, we had covered about the software and we had covered about the real-time application using this software. In this follow-up training webinar, we are actually more focusing on the hands-on training. So I will be modeling a simple concrete gravity dam. And then I hope you can all follow with me, and then you can create the model along with me. So in the next 1.5 to 2 hours, so if we can able to create a simple model and interpret the results, that will provide us with a good hands-on training experience with the software. And I hope each of you are able to install the software and they're able to open it. So is software ready with everyone so that you can follow the instructions that I will be showing you on the screen, and then you can able to create the model. I will start. So I will start creating the model, and then we can we all can go through it together. So if you have any questions in between, you can drop a question, drop a comment on the question. We can have a discussion at that time. And if you're unable to follow, please let me know as well, so that I will go back to the previous step and accordingly. Okay, let me share my screen at first. Okay, so this is the follow-up training follow-up training webinar series, and the topic is a concrete gravity dam. And we are doing a simple 2D modeling and the corresponding analysis in this meeting. So the contents for today's a training series is the follows. So first thing is we will talk about the problem statement So I will show you what I'm going to model and what you will be modeling along with me. And then in the next step, we'll go through the inputs. So what are the material input properties that we are considering, and what are the loading and corresponding definitions? So loading conditions, what are the various loading conditions that are present according to the ANCOL guidelines, and what are we considering today? So that we will be explaining. And then I will show you what are the different loading conditions that was considered in this analysis. And then we will go through the entire workflow. So this is a general workflow in FEA NX or the any FEM software, but most probably this is well suited for FEA NX. So we will go through all the process. We will start the geometric modeling, followed by materials and definitions of the properties, meshing, loads and boundary conditions, stage definitions, and run the analysis. So this is the workflow. So in the third part, we will go through each of thing. Like I will do the modeling right in front of you, and then you can copy me, and then you can please replicate the same on your PCs. And then once the analysis is done, we will check the results. So we will see what are the principal stresses and what is the factor of safety against sliding and so on. These are some results that we will be seeing. And okay, so I have the analysis ready with me as well. We can have the discussion once the analysis is done at your end as well. So that's the result interpretation part. And then, yeah, then we can have Q&A if you have any, or you can actually post the questions during the meeting as well. So let's go through the overview. So let's understand what is the problem statement that we are going to consider in today's training session. Okay. Sorry. My bad. Okay, this is the modeling. Yeah, I hope you can see my screen, right? Okay, so let's proceed with the overview. So this is what I'm going to model today. So this is the problem statement. So we can see a simple 2D analysis that is going to be done for a concrete gravity dam. The first thing is we will create this simple concrete dam, which is of height of 30 meters. And we are going to consider normal water level, which is at around 27 meters of total of a head. And then 5 meters of tailwater head. And the dam dimensions are as follows, which is 18.5 meters in depth, and then 5 meter in the top, and we have 3 meter freeboard, and then we have the downstream slope, which is like 1 horizontal and 2 vertical. So this is the general model. So in order to run this analysis, there are various ways, right? We can simply create only this dam, and then we can apply some boundary conditions at the base of the model, like presenting only compressive springs or more or completely fixed conditions. So whatever we feel like, we can do that analysis in general structural softwares as well. Even we can do the same in FEA NX. But here we are going to consider the rock and structure interaction as well. So we'll be modeling the rock, and the dimensions of the rock is around 50 meters and in depth, and then the width will be like 100 meters. So that's the idea. So we will be modeling this particular model in this webinar series. So if you're comfortable, you can draw this or take a screenshot of it so that it will be easy for you to like follow through, because we are going to draw this entire dimensions manually from scratch. Okay, it's better if you can take the screenshot of this. Okay, so I'm now moving forward. Sorry. Yeah. So let's talk about the next thing, which is the inputs. So These are the inputs that I'm going to consider for concrete and for dam. We are going to use a simple, like we are going to use a concrete material, and for rock we are going to use the rock which is of moculum material. So these are the properties. So the material models for concrete and rock are as follows. So for dam we have concrete, and for foundation we have rock. And for concrete it is an elastic material which we are considering. So and for rock we are going to consider moculum material. So this is for a preliminary assessment, since we want you to start initially. So we are going ahead with elastic and moculum material. But suppose, let's say you wanted to consider more behavior of concrete, such as not just elastic, but you wanted to consider plastic nature of concrete. In that case, maybe we can you can proceed with some other materials like one moises or Tresca, or maybe if you wanted to consider the crack propagation in the concrete, then we can go with concrete smeared crack or concrete damage plasticity, which was which I explained in the April 2nd webinar with Engineers Australia. So that's the idea. So here in this particular training series, we are going to consider a simple model with the elastic condition. And for rock, instead of going with elastic material, we'll go with moculum material. Okay. So here in the moculum material, these are the properties. So for elastic modulus of concrete, it's almost 2 into 10 power 7 to multiply 10 power 7 kilonewton per meter square. And this is almost equivalent thick, equivalent stiffness rock material. Because let's say if for the concrete dams, most of the times we rest the dams directly on the bedrock. So here we got a very good rock. And then the Poisson's ratio is 0.2 and 0.2 for both rock and concrete. Unit weight is like follows: 24 kilonewton per meter cube and 22 kilonewton per meter cube. So we are going to consider elastic properties for the concrete, right? So hence there won't be any nonlinear properties such as cohesion, friction, and tension cutoff. So these are all not present in the elastic material, but these are present in the moculum material. So we have 200, 37, and 0 as these are like nonlinear material properties in this rock or foundation. So that's what we will be considering here. And this is the loading option. So we are going to consider the hydrostatic pressure on the upstream side and tailwater pressure on the downstream side. So hydrostatic pressure is nothing but in this condition is like 27-meter head. And on the tailwater, we have like around 5-meter head. So which we'll be modeling as a pressure. So we are not considering any water water levels or something like that. We are just modeling it as a direct static pressure. So if you want to consider any pore pressure, even in the dam or as well as foundation, we can do that as well. So we can actually create the water level, supply the head, and thereby the software will be able to generate the pore pressure, both in dam and the foundation. But in this analysis, we will be only considering the hydrostatic pressure on the upstream side, and on the downstream side, tailwater pressure. So the tailwater pressure is like 5-meter head, and hydrostatic pressure is like around 27-meter head. So that's the idea. And the uplift pressure, so we are going to consider that as well. So this is the loading. And let's move with the workflow. So this is the general workflow in any FEM software, okay? In FEA NX, we are going to consider the same workflow. So firstly, we will create the geometry. And we're going to create the geometry from scratch. We will be using all the functions that are present in this software for creation of the dam and foundation. And then we will move on to the material definition, wherein I'm going to define the material for dam, which is concrete, and for rock, basically for foundation, which is rock, and elastic and moculum material. And then we are going to define a property. So here we are going to run a simple 2D analysis, right? So hence for both concrete and rock, we are going to use a plane strain condition. You might ask me like you wanted to go for a plain plate element or shell element for dam. Generally that might not be suitable because plane strain condition works well for the dam, and the degrees of freedom of a shell element or plate element is different from that of plane strain element. So hence the behavior would be different. So the concrete gravity dam is mostly a plane strain condition. Hence, it's better to consider plane strain property. So we'll define the 2D analysis for plane strain condition for both concrete and dam here. And then we will move on to the meshing, wherein we discretize the entire geometry to a mesh, wherein I will be using around a 0.5 meter mesh for the dam, and for the rock, maybe 1 meter mesh. So that's what I will be using here. Then we will apply loads and boundary conditions, run the analysis, get the results. So this is the general workflow. So let's move to the software. Please open the software at your end. So please take your time and open the software. So when the software is open, click on the new project in the top left bottom, top left corner. You can see new project. So click on there, and then the software will ask you to choose between 3D, 2D, and axis symmetry. So in this training session, we are going to consider 2D. So when you click on 2D, the direction of gravity automatically sets to Y. So please consider a 2D analysis for today's session. So let's consider 2D as model type and gravity as Y. And by default, the gravity of like acceleration due to gravity and plane strain thickness, thickness is fixed to 1 meter. So that means we are modeling 1 meter of the dam. That's what we can assume. So plane strain condition, only 1 meter of the dam thickness and the foundation thickness. That's what we are going to model. So please choose 2D and then press OK. Okay, now we can see this is the entire work plane that we are going to work on. So it is XY work plane because this is 2D, and then we are going to only work on XY work plane. You can actually rotate this entire work plane in 3D and actually see your model in 3D as well. But the analysis will be only performed for 2D. Just click on a front view in here. So this is a ribbon menu. This is a ribbon menu. All the options like the geometry, meshing are properly segregated. And we'll be choosing the geometry tab at first, wherein we will define entire the dam and foundation. Then we will move on to meshing, wherein we will define the concrete and foundation materials, followed by meshing it. And then we'll choose the options in the static analysis tab. So in this session, we are only running simple stress analysis. So hence we'll choose the options in the stress static analysis tab. So these are the three major tabs that we will be working on. And below to this ribbon menu, we have one more menu wherein we can simply rotate the model, or we can simply go to isometric view or front view or back view and so on. So there won't be much necessity for it because we are running a simple a 2D model and a plane strain condition. So just front view would be enough for you. And you can scroll your mouse to zoom in and zoom out, so which will be helpful for you later on. And in the second menu, as I was saying, we have a grid here, define grid option. So this is the define grid option. So right now, your grid size is 1 meter. Okay, so your grid size is 1 meter. And we have a total length of grid like around 20 meters, right? So if you want to change the grid, we can actually increase the size as well. So we can simply go to define grid option. And let's say the width is 2 meter. Go to define grid option and input the width as 2 meter and press OK. So thereby now the grid size is 2 meters now. So what happens with this is if you are convenient, let's say I will go to polyline, I can input the location irrespective of the grid, or else if you want to play around with the grid, you can actually simply click based on the grid sizes. Like we can click the entire model as per our need. So that's the idea. So some people prefer directly using the grid. Some people prefer inputting the values. So here in this session, we will be inputting the values. So that's the idea. So let's go with the polyline option. So in the geometry tab, under points and curve group, you can find the polyline. Under geometry tab, under points and curve group, we can find polyline option in the second row. So let's go with the polyline option. So now we are going to place the dam at the center. The heel of the dam will be at the origin, okay? And then from origin, it will be 30-meter top and 5-meter width in the top, and then 3-meter downwards, and then the downstream slope, and then covering the entire width of the dam of 18.5 meters. So that's the idea. So what we will do is, in the location, input 0, 0, input 0, 0, which will be my heel location of the dam, and press apply. Then, related to the first 0, 0 position that we have inputted, we can provide the height of the dam. So the height of the dam is like around 30, which is in Y direction, and then in X direction, it is 0. So the distances, we are going to input the relative distances, dx and dy, right? So hence, it's 0, 30. The height of the dam is 0, 30. So you can see a line has been created already, right? Then from here, we are going to provide a next, the top width of the dam, which is like 5 meters. And this is going to be in X direction. So we are going to provide 5, 0. So this is the top of the dam, which is now 5, 0. Now, in the next next point would be somewhere over here, which is 3 meter. So now 0, minus 3. So we are now defining the top portion of the dam. We define 30-meter height of the dam, and then 5-meter width of the dam on the top. And then from there, it will go down by 3 meter. So input 0, minus 3 and press apply. So now you can see another position, which is another line which was created. And this is of 3-meter width now. And from here, your dam will rest somewhere over here. And then the as we have understood that the slope is like 1 meter in horizontal, and let's say the slope is 1 time horizontal and 2 times vertical. So it's 1:1 horizontal to 2 vertical. And then I calculated the values, which will be somewhere 13.5 in X direction, comma, and depth is 27 meter, minus 27. So input 13.5, comma, minus 27. And press apply. So you need to input 13.5, comma, minus 27 and press apply. Anywhere during modeling, if you had done something wrong, you can always click on back so that the software will change the previously generated line. So now I clicked on back, right? So hence the line that was created previously went off. So what I will do is I'll input the values again, 13.5, comma, minus 27. Press apply. Then we need to cover the bottom portion, right? Bottom portion is of 18.5 meter width, right? So now what we will do is minus 18.5, comma, 0. So now the line is now here, and then we are going to input minus 18.5 so that it will reach the heel position and it will stop. So input 18.5, basically minus 18.5 and 0. Press apply. So you can see the entire dam boundary has been created now. So this is what the simple geometry model of the dam can be done using the polyline option. What we had done is we went to the geometry tab and then went to the point and curve group, wherein we can find polyline option. and use this polyline to create the entire entire boundary of the dam. So here, first point we went with the hill, which is 0, 0. And the second point we went with the depth of the dam, which is 30 meters. So hence we inputted 0, 30. And then we inputted 5, 0. And then we inputted 0, -3. And then we inputted like 13.5, -27. Then we got the downstream slope. And then we can input the base of the dam by inputting -18.5, 0. So this should be the output that you can expect from your model. Okay, so then now the next step is to model the foundation. Okay, so now let's go with the same polyline option. Since you clicked on apply, the polyline tab is still here. Had you clicked on OK, the polyline option polyline tab might have closed. You can again go to the polyline and you will find the same tab again. So now let's create the foundation by using the same polyline option. The start location is 0, 0. Again, we are going to start from here. The foundation width we are going to model is like 50 meter on from the hill, which is 50 meter. And then again, from on the other side, we are going to model 50 meter. From this way, we are having 50 meter on from the origin. On left side is 50 meter. On the right side, it is 50 meter. Okay. So input the dimension of the upstream, the upstream model of for the foundation, which is -50, 0. So we need to input -50, 0 and press apply. Oh, sorry, my bad. You can click on back. Sorry, my bad. You can click on back. The first point we're going to input is 0, 0. Okay. So input 0, 0, and then press on apply. So from 0, 0, we need to go with -50, 0 and click on apply. So now a line has been created, as you can see here. Then depth of the dam, depth of the foundation that we are going to model is again 50 meters. So from here, we need to input a 50 in y direction. So 0, -50. 0, -50. Input 0, -50. Then the total width of the foundation is 100 meters. So from here, it will be coming until here, which is 100 meters. So what we will input is location as 100, 0. In the location, in the dx, which is the distance from this point to other point, which is 100 meters, and dy is 0. So we are not providing any dimension in y direction. Press apply. So now the width of the dam foundation has been created. Then the next step is to complete this particular part, wherein I will be wherein the width of the depth of the foundation is 50 meters. So keep location as 0, 50 and click apply. So then we need to complete this particular foundation by clicking until here. And you can actually use your cursor and then directly click over this particular point. Otherwise, you can input the value as -31.5, 0, -31.5, 0, and press apply. So it reached this particular position, right? And then you can simply press OK. So this is the model that we have created until now. So this is a geometry of the dam section that we are going to run this in this training session. The top part is the dam, and the bottom part is the foundation, concrete material with elastic property, and then a foundation material with Mokulum property, the rock material. I hope everyone is following me until here. Let me know if you have any question or if you're facing any problem until here. Okay, and the next thing is now you can see this dam by selecting by simply using your cursor and selecting all the lines. Now let's say I no longer interested in seeing the work plane or maybe axis. Let's say if you don't want to see the work plane, this one and the axis, you can simply go to this work plane, show hide grid. You can click on the grid and then you can click on the axis. So this is what you will end up with. So it will be easy for you to see the model in a good way. And if you want to keep the background of your model to be white, then in the right top corner, you can find background wherein you can choose white. You can choose image white. Okay, so this is the model that we have created. So that's the first step, which is the geometric modeling, and we are done with geometric modeling. Then the next step is to proceed with the material definitions, right? So let's go with the material definitions. So this is the material definitions that we are going to provide. So we are going to use a concrete for the dam as elastic material, and we are going to use rock for the foundation as Mokulum material. And these are the values which I will be saying while inputting. And if you want to have it, you can actually take the screenshot of it and input it without my interference. Okay, let me directly input the values. Firstly, let's go to the mesh tab. Next to geometry, you can find mesh tab. In the mesh tab, we can see a group called properties, CSYS, and function, right? Click on material. Under mesh tab, you can find material. Just click on material. And then we can see create a drop down. So just next to the create, we can see the drop down. So we have a lot of materials here. So we can define isotropic material, we can define orthotropic material, 2D equivalent, interface, and sloshing medium. So there are a lot of materials. So here we are going to define elastic and Mokulum, which are basically isotropic in nature. So hence we will go to isotropic materials. Right now, first we will define concrete. And as we discussed, we are going to consider concrete as elastic material. So hence, in the model type, select elastic. In the model type, select elastic and give the name as concrete. And give the name as concrete. So here you can see a lot of tabs. First one is general tab, wherein the elastic properties will be defined here. And then we have thermal properties. So if you're dealing with any heat transfer analysis, or if you're dealing with the heat of hydration similar analysis, then thermal properties will be very much helpful for you. But right now we are not even considering thermal analysis. Then we have time dependent, which is creep. If you wanted to consider the time dependent properties of concrete, then you can actually use the time dependent creep formulation. And then we have temperature properties as well. So again, if you're dealing with time varying thermal properties, suppose let's say because of fire, because of internal heat that was getting generated, the elastic modulus will be different. And you know the temperature versus elastic modulus function, then you can actually use those functions here. So these are all for more detailed analysis. And then you can see structure tab here. So if I switch off this structure tab, then another tab would come, which is porous nature. So Structure tab implies here as non-permeable material. And then if you switch off the structure tab, you can find porous nature. So in this analysis or in this section, we are not considering any permeability of the soil or permeability of the rock or concrete. We are just going to consider simple structure model, which is impermeable material. So hence switch on the structure part. Now the elastic modulus is 2.67 E7. So which is nothing but 2.67 and multiplied by 10 power 7. So we can simply input 2.67 E7 in this software. And then Poisson's ratio is 0.2. So make sure that you are using kilonewton, Newton. Oh, wait a minute. Bad. Okay, so my bad. I'm using Newton per meter square, which is not correct. It is better to convert the units. So I'm switching off the material tabs. And then in the right bottom, you can actually see the units. So I'm going to consider kilonewtons. So right bottom, you can go to the kilonewton and then change the units to kilonewton. So now I'm using kilonewtons, meter, and then joules and second. So joules and second are not needed for me because we are not considering any heat or time dependent properties. We are only considering the simple stress analysis wherein kilonewtons and meters should be sufficient. So please go for kilonewton and a meter as the units. So this is what I'm going to consider in this training session. So once you fix the units here, then go to the material. Under mesh tab, you can find material, click on material. And then, as I said, the material properties, we are going to consider elastic material. So we'll go to isotropic and then select the model type as elastic and then give the name as concrete. And then elastic modulus of concrete is 2.67 E7. The elastic modulus of concrete is 2.67 E7. Poisson's ratio is 0.2, and then unit weight is 24. So these properties are actually sufficient for the simple stress analysis for impermeable or non-porous condition. So this is, this is my entire inputs for concrete material. Then click on apply. So now you can see the concrete material has been registered in the left window. Then the next step is to input the rock material. So for rock, we are going to consider the model type as moculum. So go to model type, and then in the drop down, you select moculum. So there you can see there are a lot of material models. So based on your needs, you can choose the different material models and then run the analysis accordingly. So for now, we are going to use moculum material. So click on moculum and give the name of the material as rock. So give the name of the material as rock. The elastic modulus of this rock is 1.86 E7. The elastic modulus of the rock is 1.86 E7. And Poisson's ratio is 0.2. Unit weight is 22. So make sure the units are in kilonewton per meter square for elastic modulus, basically SI units, kilonewton meter. So elastic modulus is 1.86 E7. Poisson's ratio as 0.2, unit weight as 22. Then we'll go to the nonlinear tab. So if you see, since we selected moculum, we are able to find the nonlinear tab of the nonlinear tab here. And this nonlinear tab, you can consider cohesion, friction angle, and so on. Cohesion value here is 200. So the rock cohesion that we are considering here is 200 kilonewton per meter square. And then friction angle, we are going to consider 37 degrees. 200 cohesion and friction angle of 37. And then we are going to activate tension cutoff. So molecular material is applicable here for rock, and we make sure that a rock has rock is a non-tensile material, and we are making the tensile cutoff. So let's consider the tensile cutoff, and it calculates on the basis of yield surface that was generated. So let's say we are going to consider yield surface as Ranikin. So what happens here is we will find some principal stresses in the model. If that principal stresses is greater than let's say the value that we enter here in a tensile strength, then it will make that value to be 0. So the Ranikin theory applies in such way. So it calculates on the basis of major principal stress here. The pressure theory works as a mean of all the major principles, all the principal stresses. So if the principal stress is greater than the value that we input here, then it will make the principal stress to that value. So if it is 100, then it makes 200, and it will not be greater than that 100. So we are limiting the value here. So keep tensile strength as 0. So that means that we are limiting the tension that is generated in the rock to 0. So that's the idea. And press OK. So now the rock is defined and the concrete is defined. So the materials are now defined. So let's close it. So that's the second step. The first step was the geometry definition, and the second step was the material definition. Now the next step is the property definition. So here we can see the properties. So let's click on the property. And in the drop down, you can choose 2D. So let's choose 2D in the drop down. Okay. So we are going to consider plane strain condition. So first thing, consider the plane strain condition. And in the drop down, select concrete. Drop down, select concrete, and give the name as dam. So this property of material concrete is applicable for dam here. So we are selecting the concrete material and giving the name as dam. And click on apply. Then select the material that we defined, which is rock. The rock material is defined, and give the name as rock. Press OK. So now make sure that you selected the proper properties in the material definition. So if you want to define or modify them, just click here, double click, and it will be open, and you can cross check it. For dam name, we provided the concrete material. For rock name, we provided rock material, which is correct. Okay, so the third step of property is also defined now. So I hope everyone is following until here. So the next step after definition of the property is the meshing. So we will proceed with the meshing. So let's go with the meshing tab. So let's go to the mesh tab, and we have an generate option. So what we will do is we will go to this generate group and click on 2D. So we are going to mesh the dam, and we are going to mesh the foundation as well. So let's go to 2D. In the generate group, let's go to 2D and click on auto create. Sorry, auto area. So since this is not the surface that we have selected, but rather the boundary, so these are just the bonding lines. The surface is not actually selected. Okay. Just for your reference, you keep this tab open, but I will show you something else to make sure that all the geometry that you have created is actually proper or not. For that, this is just for your reference. We'll go to the geometry, and then to check whether the entire geometry that we have created are properly meshable or properly able to have a surface and there are no gaps. In order to check that, we have an option called Edge Domain in the Remove Modify of Geometry tab. So we will select all the curves. So here we have a Select All option. So we will select all the curves, and all the curves are selected, and we'll click on Check. So when you click on Check, if this kind of domain is actually present, so you can see the entire geometry is closed and a meshable domain can be created. So for dam as well as foundation. So if this is created, then that means your model is good for proceeding for meshing. If it is not created, then we need to modify your geometry and proceed on with the meshing and so on. Okay, for now, that's a trick where if you are importing some geometry from your AutoCAD, or if you're importing or if you're creating by yourself, in order to check that particular geometry is properly interconnected or properly modeled without any gaps between them, then this option would be very much helpful to check whether they are properly connected or not. Then go to Mesh tab, and then in the Generate group, go to 2D and click on Auto Area. Click on Auto Area and select the entire geometry for the dam. So select the dam geometry now. And we'll give the size as 0.5 meter. So select the size as 0.5 meter. And in the drop down, we will select the property as dam. So select the property as dam and give the name as dam. So now in the mesh set, we can directly write it in using the keyboard, and then the name of the dam will be appeared, and you can simply click on apply. So you can see the dam mesh has now been created. So you can see this mesh which is created in the models workstream. This is the workstream. In the model group, you can find the mesh which is as dam. So now the next step is to mesh the foundation. So again, in the click on select edge here. Then we will select the entire foundation. So select the entire foundation. And we'll give the size as 1 meter this time. So previously we went for 0.5 meter for dam, but for foundation, it's not that important to go for very finer mesh size. Let's go for a reasonable mesh size of 1 meter here. But here under the properties, select rock and give the mesh set name as rock and press OK. So the meshes are now created. So the third step, which is, the fourth step, which is meshing, is now done. So the mesh for the dam and the mesh for the rock is now created. Everyone, I hope, is following. So now you can see dam and you can see rock. So if you click on this mesh, you can actually find which property is assigned here. So we can see the concrete material is assigned, and for rock, you can see the rock material is assigned. Okay. The next step is to create the interface between rock and the dam. Okay. But before creating the interface, we can actually provide the boundary conditions and the loading conditions as well. Okay, let's keep the boundary and loading conditions as next step, and we will only create the properties for the interface now. So here in the mesh tab, you can find the element group. So this is the element group, and we have an option called interface. So let's create the interface between rock and the dam, and we need to define the limiting of tension for tension crack behavior in this interface definition. Okay, so for that, let's go to the mesh tab, and go to element group, and go to interface. And interface, in the interface, we'll go to the line interface. So here, the interface between rock and the dam is actually line. So hence, we need to, this is a 2D model, and the interface here is actually a line from here to here. Had it been a 3D model, we needed to go for plane, but now it's a line, right? So hence, select from the element boundary, and we need to provide the interface between dam and the rock. And this dam is only in contact with the rock. So hence, selection of element boundary would be fine. Like, let's say if this dam is in contact with this some other soil or rock on the left and right hand sides, then the interface would be created on all those sides as well. But let's say you wanted to only create between dam and foundation. In that case, you can go with from mesh set as well. So whatever you feel like. For this condition, you will have the result output same from the type from mesh set or from element boundary. Both ways you will get the same result now. Okay, let's go with from mesh set in the drop down for interface creation from mesh set. And we will select both the dam and foundation. So we selected both dam and foundation. Then click on wizard. So we are going to ask the software to calculate all the stiffnesses between the dam and the rock by itself. So click on wizard, and we will use the strength reduction factor. So we can see the strength reduction factor as 0.8. So you can actually go through our help manual to understand why I kept 0.8. So it depends on the material. If it is concrete and rock, it ranges from 0.8 to 1. If it is clay and concrete, it ranges from 0.6 to 1. So the ranges are present in the help manual of this software. So use the strength reduction factor as 0.8 here and press OK. And click on OK. So now you can see an interface is created in here. And we can find the line interface and the rigid link mesh sets as well. So now we will see what definitions were created by the software for interfaces. So for that, we'll go to property, we'll go to material tab in the mesh ribbon menu, go to material, and double click on the interface material. So this is the interface definition that was created by the software. So we have normal stiffness and shear stiffness, which is automatically calculated based on the stiffnesses that we had defined for rock and concrete. So we defined some elastic modulus for rock and concrete, right? So that will be automatically considered for the creation of the interface stiffnesses K and KT. Okay, let's save this model file somewhere. If this kind of thing is popping up on your screen, please save it somewhere. Okay, so these are the definitions. So we can see the normal stiffness automatically created, shear stiffness automatically calculated, and the cohesion and friction angle are calculated for the interface. Okay, then this is the important part. We are limiting the tensile strength to 0. So this is already considered. If it is not considered, please activate it and then keep a 0 value. Okay, so tensile strength as 0. Which means brittle nature. That means just whenever the tensile strength is happening, that element has no capacity to take any more tension and it will fail. That is what that brittle nature is implying over here. So tensile strength to be 0. And we have more functions for hardening conditions as well, for even for interface. But for now, we are only considering brittle nature, which is tensile strength 0, and the material is considered as failed. And then press OK. So what happens with this definition is whenever there is a tension happening at the dam and the rock, that means that is getting separated. So that element is failed. That means the interface element is failed, and the dam and the rock will now be separated. So that's the idea. Now let's close this. So now the interface definition is also done. And what we had done is we created a geometry followed by material definition, followed by properties, followed by meshing, and followed by interface creation. So these are the steps that we actually followed. And the next step is boundary conditions. So go to static analysis. So we are running a simple stress analysis, right? So hence we will go to static analysis tab. Here we will go to constraint. In the boundary group, click on constraint. In the boundary group, click on constraint. Go to auto. So the software will automatically create the boundary conditions for you. So hence go to auto. And we'll give the boundary set name as ground support. So input the boundary set name as ground support and press apply. So what the software does here is on the left and the right hand sides, it provides normal restraint. That means this particular elements on the left and the right hand side cannot move in X direction. So it is normally restrained, but it is okay to move in Y direction. So that it might settle, but it might not move laterally, only on the boundary nodes. Okay. At the bottom, it is fully fixed. In the bottom, it cannot slide, or it cannot settle, or it cannot move laterally. So that's the definition. It's completely fixed at the bottom and only normally restrained on the sides. Okay, so that's the definition that we are providing. And now the ground support is done. We can simply click cancel here. The next step is the loading definitions. Okay, so let's go for loads. First step is we'll go for loading definition. And before going for loading definitions, I will show what are the loading conditions that we have and which one we are going to consider in this analysis. So let me open my PDF. Okay, here we go. So these are the loading conditions that we need to assess the dam for these different loading conditions. So we have a normal operating condition, we have flood condition, we have earthquake, we have extreme loading, and we have post-construction and maintenance conditions. So these are the different conditions. And we are going to consider only SLS for this analysis, simple analysis with serviceability conditions. And we have dead load, we have hydrostatic pressure, we have uplift pressure, and this S represents silt pressure, and so on. So you can actually consider all these analysis in this, all these loadings in this software, but we will be only considering the uplift load, a dead load, and hydrostatic pressure and tailwater pressure. So that's what we are going to consider for this simple analysis. And again, I will show the loading conditions. So we will consider self-weight. This red dot represents the self-weight, and we are going to assign hydrostatic pressures, and we are going to assign uplift pressure and tailwater pressures. Okay. Let's go back to the software. At first, let's assign some self-weight. In the static analysis tab, you can find static load. Click on self-weight. So click on self-weight. And by default, it is in Y direction, negative Y direction. Okay. And which is what we needed. And give the load set name as self-weight. So we defined unit weight for all the materials, right? The software will be able to calculate the unit weight for each and every element and each and every location, and it will automatically apply. No need to worry about it. So hence we just define the global self-weight. So click on the self-weight option, and then input the load set name as self-weight and press OK. So here we go. This is the load set name. Then let's define the hydrostatic pressure. So we'll go to the static load tab and then click on pressure. So go to static load tab and click on pressure option. So these are all normal pressures that we are going to assign. So select the upstream faces of the dam. So that's where we are going to assign now. So go to static load and click on pressure. So first thing is you zoom in into the model, and then select the base of the dam. Okay, so not base, sorry. Select the surface of the rock on the upstream side. So select all the surface of the rock. You can see all the surface of the rock, and even this particular portion. So maybe it might not get selected. You would get around 50 objects. So hence, this is of a 50-meter width on the upstream face. And then we had provided 1 meter mesh size. So hence you will find 50 edges. So select all the 50, all the bottom surface of the upstream face. Then select all the upstream faces of the dam as well. So something like this. So you can select the upstream face, zoom in more, and then select the rest of the mode as well. So you can zoom in and zoom out to be able to select the entire uh, upstream face of the dam as well as bottom face, the top face on the upstream side of the rock. I think you will end up having 110 objects. Okay. So if you are having more objects, make sure nothing has been selected at the dam and rock interface. So if that is selected, that means you're having you're providing some external force at the interface of the dam. Okay. So you will end up having 110 elements, 110 faces, objects here. Then here, the thing is we are going to consider hydrostatic pressure, right? So the height of the dam, so the height of the normal water level is like 27 meters. And that means from origin, we are going to have the load at 27 meter. So at 27, we are going to have zero pressure. It's a triangular variation because of the water load. At 27 meter, we will have zero pressure. But at depth 0, we will have 27 multiplied by 9.81, or maybe let's consider unit weight of water to be 10, which is 27 multiplied by 10. Multiplied by 10, and we will have 270 at zero depth, right? So that's what we will be going to define now. So let's click on this base function and click on this particular option. Right, so this is the new tab that you will be able to see. And then what we can see is the load is varying, right? That's a varying load from top to bottom, which is along y direction. So hence, independent variable should be y. Okay, we need to make sure that independent variable of y is selected here. And then we'll give the name as hydrostatic pressure. So if you have some equations, like let's say you're dealing with hydrodynamic forces via Westergaard's equation, we can actually input the entire Westergaard's equation here. The software will calculate the values for you. But here, this is a very simple calculation. So hence, we will provide it by ourselves. So first thing is at 27 meters, okay, we'll input 27 meter in the first row. The value at 27 meter is 0, okay? And then click on tab on your keyboard, wherein at depth 0, you will have 270. That means 27 multiplied by 10 unit weight of water. We will have 270 kilonewton per meter square of pressure. So this is the varying pressure that you are providing. So at 27 meters, it is 0, but at 0 meter, it is 270. So then click on the next row. When you click on the next row, you will be able to see the graph that was plotted. So this is the graph that was plotted, and then click on apply. Right now, this entire definition was created. Now you can close this, close the tab, and in the drop down of the base function, click on hydrostatic pressure. Okay, the values that we have inputted in the base function is dimensionless. Okay, or dimensionless. The values that we inputted are dimensionless. So we need to provide dimension and the units here. So hence we will multiply it by 1 kilonewton per meter. So hence the units will be assigned to the values that we have inputted in the base function. So this will act like a multiplier here. Okay, then in the load set name, we can define it as hydrostatic pressure. And press apply. So you can see the load is defined on the upstream face of the dam, as well as the top face of the rock. So you can see this is a triangular variation. So it starts from 0 and then it ends at 270. So even though you had selected all the upstream faces of the dam, you will be able to see that still the load is getting applied at 27 meter only. Okay, that's how it works. So now the next loading condition, which is, let's say, the tile water pressure. The tile water head is like around 5 meters. Okay, so what we will do is we will go onto the tile water pressure. So we will select more height of the upstream faces of the dam. You can select like just above 5 meters. We need to select anything. The software will be able to apply load only from the 5 meters. So you can select all the faces on the downstream side, or more faces. Let's say more than half, like this, and then make sure that all the upstream faces is selected and not any interface edges are selected. Okay, and select all the downstream face of the rock. Select all the downstream face of the rock. So this is how select the tailwater pressure. This is the area where in which the tailwater load will be applied. So what you will do is select the major portion of the upstream, downstream face of the dam, and select all the downstream faces, and make sure that you're not selecting any of the elements on in the interface. So if you had selected, if you click on the same selected element, it will get unselected. Then select the downstream face of the rock. Okay. So now we'll go to the base function again. So we will define the base function for the tailwater pressure. So select this option again. And the next thing is, again, the independent variable is y. Okay, independent variable is y. And we'll give the name as tail water pressure. Tail water pressure. And here in the y, in this particular function, let's define the values. So at 5 meters, which is the head of the tailwater pressure that we are considering, we have 0 value. But at, let's say, at 0, we have 5 multiplied by 10, which is 50. And then click on the next tab. Okay, delete. If there is some value already getting created, you click on this option. You click on the left-hand side, and you can simply click on delete on your keyboard. Okay. So now the tailwater pressure is 0. At a 0 depth, we have 50. And at a 5 meter depth, we have 0. So that's the tailwater pressure. And then press OK. Now, in the base function, select the tailwater pressure. In the drop menu, drop down, you can select tailwater pressure and press and for under pressure, you give the value as 1 kilonewton per meter. So this will be acting like a multiplier for the load that we had applied. So now let's apply 1 kilonewton per meter as a multiplier, and then select the base function as a tailwater pressure, and give the load set name as tailwater pressure. And actually you can preview it. So let's say here, this is the option for preview. Before clicking on OK, you can preview it. So click on preview. You can see, even though I had selected a lot of element faces on the downstream side, the software will only apply until 5 meter. So this is how the software would work. So now we have the load only until 5 meter ahead. So this is the preview option. You can actually preview it before clicking on OK. Now you can simply click on OK. So that's the tailwater pressure. I hope you guys had provided both tailwater pressure as well as what do we say, the hydrostatic pressure, right? Now the next thing is to assign some uplift pressure. So for the definition of uplift pressure, I would ask you to hide the foundation. I would ask you to hide the foundation. To hide the foundation, in the left-hand side, you can find model works tree. You can find model works tree like this. You can find model works tree, and you can find mesh. You can find mesh. And in the mesh, you can actually click on this drop down, and you can see all the meshes that we had created. We will hide everything and only unhide the dam. So we only make sure the dam is highlighted here. Okay. So unhide everything and only activate the dam. So unhide everything and make sure that only dam is highlighted. Okay. So now let's go to the pressure option again. Go to static analysis tab, go to static load, and then click on pressure. So let's say there are no drains here. So hence it is going to be a continuous varying load with no abrupt like reduction in the uplift pressure. So that's what we are considering here. So what we will do is we'll go to a static load and go to pressure and select all the bottom faces, bottom element edges of the dam. So you can see all the bottom element edges that were selected. You will end up having 37 objects selected. Make sure that these edges are not selected again. Only the bottom edges of the dam are selected. So select the bottom edges of the dam. You can actually zoom in using your scroll button and zoom out. It will be easy. Okay, so now go to the base function. Let's go to the base function. So let's go to the base function. And here the uplift pressure will vary along the x-axis, right? So hence the independent variable should be x. Okay. So at zero, we will have an uplift pressure of 27 meter head on the upstream side, right? So hence we will have an uplift pressure of 270. Okay. So at 0, which is my heel position, I will have a value of 270. Again, the width of the dam is 18.5 meter. So hence at 18.5 meter, we will have the value of 50, which is the tailwater head, right? So hence 270 and 50. Then we'll give the name as uplift pressure. So I'll give the name as uplift pressure. At 0, it is 270. At 18.5, it is 50. So that's how it is going to vary. You can click OK. And then in the base function, click on uplift pressure. Under the uplift pressure, under the base function drop-down menu, click on uplift pressure. Then we'll keep the value as 1 kilonewton per meter. Okay. Let's use the value as 1 kilonewton meter in the to define the dimension. So let's keep it as 1 kilonewton meter. And load set as uplift pressure. The load set as uplift pressure. Okay. Load set as uplift pressure, and click on preview. So when you preview it, you'll be able to see on the left hand side it's 270, on the right hand side it becomes 250. And then press OK. So this is the uplift pressure, hydrostatic pressure, and the tailwater pressure. Now in the mesh tab, if you activate everything, you'll be able to see all mesh sets as well as loads that were applied onto the dam. So that's the entire modeling thing until the meshing and loading and boundary conditions we are done. The next thing is to create the stages and then run the analysis. That's all. So we need to create the stages and we need to run the analysis. So let's define the construction stages now. I hope everyone is following and you're done until this part wherein the loadings were created. Any questions, please let me know. Mr. Navdeep Singh, if I think you have a question. Oh yeah. Okay, so I hope everyone is okay until here. Let's proceed on with the construction stage definitions. Again, in the static analysis tab, if you have any questions, drop it in the comments tab. We can discuss now. Otherwise, we can move forward. Okay, let's move forward. For now, there are no questions again. Okay, so now let's go for the construction stage definitions. So in the static analysis tab, we can find construction stage. Right? In this construction stage, you can find an option called stage set. So click on stage set. So this is the stage set option. And as I said, we are running the stress analysis. So in the stage type, you can find stress analysis, stress nonlinear time history, seepage analysis, all the other related analysis. But we are only concentrating on stress analysis now. So let's go to stress. And we'll give the name as, let's say, dam. So that's the dam analysis. I'm just keeping the same name, which is dam. Okay. And click on add. So you can actually run multiple construction sequences. That means you have one set of sequence to see whether it's okay or not, and you have a second set of sequence. Let's say you wanted to understand the second set of sequence as well. You can actually create multiple sequences in same model. So for now, I'm creating only single sequence. So under that single sequence, let's define all the construction stages. So let's go to this dam, which we had created. Select the stage type as stress and give the name as dam and click on add. Then you will be able to see this dam under stress type created. Then we'll click on modify. You select this dam and then click on modify. And then you need to click on define CS. So we are going to define the construction stages. Select the dam and click on define CS. Sorry for that. Select define CS. So now we will make sure that whatever is highlighted here will be shown in the software as well. Hence, you go to show data in the bottom of the tab and click on activate. So click on activate so that whatever is active in the activated data will be shown here. Okay. So right now nothing is active, hence no message is being shown on the right-hand side of the screen. Okay. So in the show data, click on activate. So now let's go to the stage name, which is in situ. Okay. The stage name that we are considering is in situ. That means only rock will be present here. So right now on the right-hand side, which you are seeing is a simple geometry that has nothing to do with it. We need to make sure the mesh sets are activated. Okay. Let's give the stage name as in situ condition. In the initial condition, we only have rock, right? So let's activate the rock. So simply right click on the rock and you can click on activate. Otherwise, you can drag that rock and then drop it in the activated column. Whichever is good for you, whichever you like, you can actually go for it. So let's activate the rock in the activated data. Then activate the ground support. So you can see the rock and the ground support is activated. And then activate the self weight. So we are going to activate self weight, ground support, and the rock. So the rock method is activated, ground support is activated, and self weight is activated. Then we make sure that this is clear, clear displacement option is activated. So because of the self weight, whatever displacement that might occur in the rock, we are not interested in that, right? So hence we'll clear the displacement. So we'll clear the displacement in the rock for the self weight and press on save. So that's the first stage. The first stage is initial condition or in situ condition, wherein the self weight of the rock is cleared. Then we'll go to the next stage. In order to go for next stage, click on new. So we are defining two stages now. Second stage now. Stage 2 is dam. Stage 2 is dam. So now in the dam stage, you can simply activate the dam mesh set. So let's activate the dam mesh set. Okay. And since dam and rock are now interacting with each other, we need to make sure the line interface is also activated. So this is the interface behavior that we had considered for dam and rock, which can simulate the tension crack. So let's activate the line interface along with the dam. Okay, so now the dam and line interfaces are activated. So there is no need to reactivate the rock because the rock is already activated in the previous stage. It will continue until and unless you make sure that it's in deactivated condition. Okay, but since it is activated in the first stage, it will remain activated even in the second stage. So now dam and line interfaces are activated. You can simply select dam and line interface and drag and drop in the activated column, or you can right click and then click on activate. So dam and line interfaces are activated. Click on save. Then click on new. So then click on new. So we have new, which is third stage, wherein we will be defining the loading conditions. Give the name as loading. Give the name as loading. And we will activate all the loads. We will activate hydrostatic pressure, tailwater pressure, and uplift pressure. So select all the loads, drag and drop it in the activated data, or else you can right click and click on activate. Now the hydrostatic pressure, the tailwater pressure, and the uplift pressure are now activated. Let's say, as an engineer, I wanted to see the gradual increase in this water pressure and thereby behavior of the dam in gradual response rather than entire 100% load acting at the same time or at a single time. I wanted to gradually see the load steps. So in order to see that, I will go to analysis control. So let's go to this analysis control. So you can simply go to the analysis control. So go to this analysis control and then go to nonlinear tab in the top. So go to nonlinear tab. This is a nonlinear tab. And I wanted to run this particular stage for 10 steps. So you input the number of increments as 10. That means whatever the hydrostatic pressure, uplift pressure, as well as the tailwater pressure that you had applied will be applied in increments for 10 times, linear increments, okay? And if you wanted to have some non-linear increments, then you can define your manual steps. But let's go for linear increments. And we want the software to save all the increments. So click on every increment. Click on every increment, okay? And then press OK. So now in this particular loading stage, we are asking the software to run this analysis in load steps for 10 times, and then every increment is saved, and then press OK and click Save. So click on Save. The construction definitions are done. Okay, click on Close and close this construction set as well. So now the construction stage definition is also done. The next step is to define the analysis case. So let's go to the analysis option in the top. Click on analysis option, analysis ribbon menu. So click on analysis ribbon menu and go to general. So in the analysis case, you can find general. Click on general. Here in the solution type, we will go for construction stage. So in the solution type, we go for construction stage. So select construction stage. So click on construction stage. And we only had defined one stage set or construction sequence, which is dam, and we need to select that only. And we'll give the title as dam analysis, maybe. And this construction stage analysis in this software is directly nonlinear in nature. So if you are running the construction stage, that means you're running a nonlinear analysis. If you wanted to run a linear analysis, then you have a linear static analysis option here, but we are doing the construction stage analysis. So then initial state, we have dam. Initial state, we have rock, and the next state, we have dam. And in the third stage, we have the loading conditions, right? In the first stage, when we have a dam, when we have a rock, we need to, let's say my requirement is to run it in under K0 condition, okay? So for that, go to analysis control. So we are going to run K0 condition for rock in the initial stage. Go to analysis control, and then we have an option called advanced geotechnical settings. So click on advanced geotechnical settings here. Once you click on advanced geotechnical settings, you will be able to see this option. Okay. So we need to activate initial stage for stress analysis. So when you activate initial stage for stress analysis, all the three stages that we have defined will be appeared here. We need to select the first option, which is in situ. That's the name we had given for the initial stage. And we are wanted to run this for K0 condition. So apply K0 and apply clear strain definition, and then click on cut off negative effective pressure. So these options should be activated. So what happens is, whenever you activate the K0 option, the software will run a linear analysis for this initial condition when the rock is activated. That means it will run a linear analysis. So if there is an, let's say, undulations in the, like it's not completely straight or horizontal, but it is inclined. Let's say the rock which you have modeled is inclined. In that case, there might be a possibility for negative effective pressure generation. So we need to ask the software to let it go. Like we need to let the initial condition and effective pressure, negative effective pressure to be 0. So we'll cut off negative effective pressure. Okay. And then let's activate the next option, which is estimate initial configuration of the activated elements. So what happens over here is, so we have 3 stages: initial stage, in situ stage, dam stage, and the loading stage. So in the dam stage, what happens is we are going to apply the self weight of the dam, and it will tilt towards the upstream face of the dam, right? and then when the new mesh sets are activated, let's say in your compacted fill method for other dam later on, then onto the deformed shape of the model, if you want to activate any new mesh set, then this option should be activated. So this is very important when you're dealing with the construction stages for excavation and filling, maybe for the NAM or maybe for deep excavations or tunnelings and so on. This is very much needed. In this particular analysis, you won't find any difference even though this is activated or not. But just to get you like acquainted, I'm letting this option to be activated. So let's activate this initial configuration of the activated nodes and press OK. OK, and here as well. So click OK on all the 3 tabs. So now the modeling is done. We are now good to go for analysis. So to run the analysis, you go to the analysis tab again. So this is the analysis tab, and go to analysis group. You can find perform. Click on perform. Make sure the dam analysis tab is activated and press OK. So now the analysis is running. I hope everyone is following until here. If you have any questions or if you are left behind, please let me know. The analysis is done on my PC. Let me know if the analysis is done in your PC as well. I hope the analysis is done at your end. We can see the results together. Okay, I hope everyone is done with the analysis, right? So kindly reply. Okay, let's see the analysis and analysis results. Okay, so now in the results tab, so I hope you can see the results tab here. Just next to the model works tree, you can find results tab. So you can see the results in all the 3 stages. So you can see the initial stage, dam stage, and the loading stage. And you will be able to see the results in all the 3 stages. So let's see the results from initial stage, okay? I want to see the results of displacement at first. Let's go for displacement here. Go to displacement, and I wanted to see the total translation. You can double click on the total translation to see the result. So right now we cleared the displacement in the initial stage, hence the results of initial stage is 0. for displacement, because we cleared the displacement because of the self-weight of the rock. Now, in the next stage, we have a dam, right? You go to the dam and then you activate the load. So you can activate the displacement. You can see this is the total translation, and you can find the dam is tilting towards the upstream side, right? So if you do not want to see the undeformed shape, if you want to see the undeformed shape, in the deform you can click on undeformed. But it's better to see the deformed shape. It's not exaggerated value. Sorry, it's the exaggerated deformed shape, but it provides us a good idea onto which side the dam is deforming. So you can see the values are very minimal. It's like 1 mm, 1.5 mm onto the left hand side, onto the upstream side. So if you want to change the units to mm, you can go to the right bottom corner, and I will convert the units to mm. So the dam is now deformed to 1.57 on the upstream face of the dam. And we have an option called probe. This is the probe option. So if you go to the probe option, and you can actually click on all the nodes at any nodes of your interest. You can see the values at each and every location. So this will be very much helpful to properly understand the behavior of the dam when you're dealing with the multiple steps. Okay. So now this is the results of the total translation. And if you wanted to see the mesh edges, then actually you have an option called edge type on the left top option, and you can see the mesh edge so that you can see the nodes and results of that particular meshes as well. So some people prefer this kind of viewing, and some people prefer only the feature viewing. So it's up to us on how to display the results. And this is a probe that was defined, and I'm just unchecking it. That's done. Okay, now the next thing is seeing the results in the loading condition, which is the loading stage, third stage. So you can actually go to the loading stage and click on the first loading and click on total translation. So now we have a displacement of 1.4. Instead of going through each and every step, you can actually scroll down this stage bar, and you will be able to see the result of each stage. You will be able to see the result of each stage, each step. So we had analyzed this loading under 10 steps, right? So you will be able to see the behavior of the dam in those 10 steps. So you can see because of the loading, the dam is displacing from the upstream side to the downstream side. So which is very much helpful for viewing and understanding the behavior of the model purpose. So initially we have a 0. And then when the dam is placed, it is displaced onto the upstream side by 1.57 mm. And as the loading of the water proceeds, we can actually scroll it down to see step by step. You can see the value is decreasing, and later on it is increasing. And the max displacement it went onto the upstream side is around 1.3 mm. So it's very less. The displacement is almost less. The dam is almost safe here. Okay. Then the next thing is to see whether the tension crack is happening or not. Okay. For that, you can actually zoom in on the upstream face or heel of the dam. You can see there is a gap which is generating between the rock and the dam. That means the rock and the dam are getting separated on the heel side of the dam, right? On the heel side of the dam, which means there is the tension crack just started because of the loading that we had went for. Had it been a ULS load, then it might be a much more deformed location. You might see much higher like movement, not just one element over here, even multiple elements might got failed. So right now, one interface element is failed under tension since the tension reached the limit of 0 when a tension crack started getting generated here. Okay. Now, as we can see, the tension crack is generated, but we want to see the values over there. So for that, what I will do is I will go to the deformed shape here. So go to the deform and click on undeformed. So I want to see the result of the interfaces, which is the normal forces as well as the sliding forces in the undeformed view. So let's say we have the interface stresses, which is normal stress, we can find it, and we can find the sliding stress, or basically the tangential stress or friction stress or sliding stress, which is with the lateral stress and the normal stress, which will be used for the calculation of a factor of safety later on against sliding. Okay, for now, let's go to the very last step, which is increment 10 at load of 1. And you can actually find interface stress here, interface stress, and click on normal X. So right now, element center result is being shown. If I deactivate this element center result, you can see that on the heel side of the dam, the normal stress becomes 0. That means since the normal stress becomes 0, the tension crack is going to get started. So until all the other locations are negative in nature, that means they are still experiencing compressive forces. Had the dam is overturned completely, then everything will be represented as tension. Right now, like only the heel portion has the tension, and hence the normal stress is 0 here. And all the other locations we have compression. So if you want to change the units back to, let's say, if you want to change it in Newton per mm square, yeah, this is what you can see. Or if you go back to kilonewton per meter square, you can actually change the units in real time, which is very much helpful in this software. So we can see kilonewton per meter square. The 0 at the heel, it's 10 power minus 12, and very maximum compressive stress of around 1300 on the toe of the dam. So this is the normal stress. And then we have tangential stress. Go for tangential Y. So you can see this is a tangential force, which is actually the sliding force. So since we have the hydrostatic pressure and the uplift pressure as well as tailwater pressure, so hydrostatic pressure is the one which is letting the dam slide, and we have around 50 to almost 950 in terms of pressure. We will see whether this is high enough to reduce induce the sliding, or if the factor of safety is greater than 1 or 1.5 over there. So that's the stability check. I will come to the extraction and the calculation at the end. But before that, let's see the principal stresses. So I will deactivate everything and only activate the dam. Okay, let's activate only the dam mesh sets. And then in the very last step, we can see the principal stresses, principal strain stresses. I want to see the major principal stresses. So let's say this is the entire dam and we have major principal stresses. The positive represents the tension, the negative represents the compression. So I want to convert this into MPa, so hence Newton and mm square. So this represents that we have a tension of 0.1 Newton per mm square, or 0.1 MPa, and the maximum compression of 0.26. And maximum tension is happening at the heel of the dam again, right? So now the tension is there, and then we have a compression. And if this tension is very much greater than the tensile limit of the concrete, then the reinforcement design should be there appropriately so that there won't be full-blown tension cracks getting generated over there. Had there be a gallery, then since the gallery is opening and we can find a lot of tensile stresses getting generated around the gallery. But for now, there is no gallery in this portion. It's NOF, and then we have tension at the upstream face of the dam on the heel. Okay, so this is a major thing that we wanted to see. But let's say I will activate all the rock and everything, and you can find more tensile stresses in the rock and more the compressive forces or major principal stresses in the rock. So we can actually see the plastic status of the rock as well. Let's see the plastic status. So yeah, here we go. All the blue color represents loading and unloading failure, but this is the important part. Here we can find tension failure. So since the dam is overturning, and since this is molecular material, we can find some tension failure. And because this area is experiencing tension because dam is moving forward, but we are limited the tension to 0. So hence the entire area is under tension on the heel of the dam. So that's the idea. Now I will extract the normal forces in the interface, as well as the shear forces, basically the friction or sliding forces, and then we will calculate it we will use it to calculate the factor of safety. So let's go back to kilonewton and meter, which will be easy for me. So yeah, I will go to the extract option. In the extract option, we choose interface stress, and I wanted to extract normal X, but only in the last step, which is loading. So I will unselect all, and I only select the last loading step. Okay, that's where all the load was present. Now I will select a node and element in the order because I have a lot of elements that to be selected, and hence the order should be via node and element. And the object that we are going to select is the element. So select all the interface elements now. So all the interface elements are selected. And then click on table. So now the normal forces are now selected here. You can right click this and export to Excel. So you can see the software is saving that as interface stresses in the folder where the model is saved. And it got exported. So let's open that input. So this is the interface stresses. Yeah, here we go. The values are now applied here. So exported here. The interface stresses, normal stresses. Similarly, we will go for the sliding stresses, which is tangential Y. So which is tangential Y. So I will go to this training FEA. You can close this interface stress. Let's go to the training FEA. That means the model where I have selected. And I'm selecting the last step. Select the node, select order as node element and object as element, and then select all the interfaces elements. Again, select all the interfaces elements. Again, click on table. So let's copy this. We can select the entire table by clicking on the top left corner. Control C. You can see 37 rows have been copied. And then we'll go to the same sheet and we can paste it here. So this one is a normal force and normal stress, and this is the tangential stress. Okay. So now this is all stresses. These are all stresses. Okay. And I wanted to convert the stresses into force. The area of the stress is around 0.5 meter mesh size and 1 meter plane strain thickness, right? So hence I'm going to multiply the stress, normal stress, multiplied by 0.5 multiplied by 1 meter plane strain thickness. So hence this is a force acting in that particular element under the entire load. So this is the entire normal forces at each and every element. Now let's go for summation. And press enter. So this is the entire total force in the dam. Let's keep the sum, and I want to take the absolute values, which will be ABS and the top value. So this is the total absolute normal force. Okay. Then we have the sliding force. So this is the sliding force. sliding stress. We have sliding stress, so hence multiply by again the area, which is 0.5 multiplied by 1. So we'll give the name sum and ABS sum, absolute sum. Let's add up every force. And then we'll give the name absolute sum as well. So this is the sliding resistance, sliding force. And here we have the normal force. Now what we will do is we will calculate the factor of safety. Let's see the factor of safety. So this is the formula. Let's copy this formula. Yeah, here we go. So these are the equation. This is the equation that we're going to calculate according to the AND code guidelines for the factor of safety against sliding. So now FOS against the sliding equal to, so the friction coefficient multiplied by normal force is what we are going to use. And the frictional coefficient of the dam and the foundation, we need to know that one, plus cohesion multiplied by area. So let's say we are not going to consider the cohesion by area, and we have the horizontal force. So this horizontal force is nothing but the sliding resistance which we had calculated. And if the normal force multiplied by friction equal to 5076, so we can simply say normal force divided by friction force. So the factor of safety is 1.44. So that's the idea. In this case, your dam is safe for SLS condition against sliding, as the factor of safety is greater than 1, which we have it like around 1.44. So that's the idea. And so hence we can calculate the factor of safeties against sliding. We can calculate the principal stresses. We can see the displacements and so on. And that's the idea I wanted to give with training. I hope you had able to calculate the interface stresses. You are able to see the displacements and so on. So if you have any questions until now, please go ahead. So this is what I wanted to show you in this training, and I hope you had followed all the questions, all the topics. Oh yeah, we have one question from Mr. Navdeep Singh. I know we have defined each element such as concrete. So he says he wanted to see the dam water condition rather than applying it as a pressure. Yes, we can do that. So if we wanted to define water rather than applying it as a pressure, yes, we do have an option. Let's go for the geometry. And I know this particular length, let's say what I will do is, we need to define the water level at first, okay? So here, we will define 27, which is my total head on the upstream face. So we will draw a line on the upstream face of the dam that represents the that is going to represent my water level. Okay, we need to draw it visually. Further, let's go for 0,27, and then minus 50,0. So now the upstream face, on the upstream face, we can find the water level. Okay. Similarly, we need to define it on the downstream face. So let's go for somewhere here, let's say. No, not this. Cancel. Let's go for this position. Let's say that is my water level, and it will be let's say 40,0. So that's my water levels on upstream side and the downstream side, let's say. So instead of considering it as pressure, direct static pressure, we can actually model the water levels by defining the water level in the software. So let's go to the static analysis tab. And here we can see water levels, okay? Click on water level, select the lines that he had created for the definition of water levels and press OK. So now the water level is internally defined in the software. Then we'll go to the dam construction stage set. In the loading condition, what we will do is, instead of giving the hydrostatic and tailwater pressure, I will uncheck them and I will go to the defined water level as global. And then I will click on the water level that I had defined and give that value of multiplier as 1. So this is the water level that we can define. So now the water level is defined and software will automatically interpolate between the two lines. So now the water level is defined in the loading stage. But how about the load that might, hydrostatic pressure that will cause according to the water level? In order to consider that, we need to go to analysis control. And then in the advanced geotechnical settings, we need to make sure that automatically consider water pressure option is activated. So the software will automatically calculate water pressure, and then we can assign it onto the model. Instead of considering the automatic consideration, we have other options such as water pressure. So what we can do is we can simply select the upstream face of the dam as well as this option. And here, let the software calculate by water level boundary. And I will give the name as hydrostatic pressure, let's say, apply. Similarly, I will select the tiled downward face. And I will give it as a TWL, let's say. So now we have water level as well as water pressure that is automatically calculated by the software. We'll go to the loading and we will activate a TWL and hydro, which I just activated. And there is no need to define the water level as well, okay? And sorry, we need to define the water level. We need to define this. There is no need to define automatically consider water pressure option in this place. So using these two ways, we can actually calculate the water pressure, and we can let the software calculate by its own rather than relying on manual calculation. We can simply define the water level, water level boundary, and we can use this water pressure function, or we can simply let the software calculate automatically in the analysis control. So you have two ways. And the third way is what we have done in this training session, which is direct application of pressure. I hope this answers your question. Nice. Any other questions? So the training is done here until now. All the things that we wanted to show is done, and I hope you guys had like followed up, and you are able to see the results that you in your PC. So if you have any questions, please let me know.
Thank you, Harsha, for a great session today. Oh, there's another question.
Yeah, we have one question. During earthquake loading, do you have a fluid element option to apply hydrodynamic loading instead of Westergaard added mass? Yes, we do have a fluid element in the software. So in the definition of the material, you can go to the sloshing medium, and then the software will define the fluid elements. And then instead of considering the Westergaard's mass, you can actually create the sloshing medium, and then the software will apply the forces onto the dam according to the all the frequency of your earthquake motion. The pressure applied onto the dam will be different because you are now defining the sloshing medium rather than Westergaard's equation. Yes, that can be considered in this software by using sloshing medium. So if you are okay, I have an let me show you a simple picture, so that will be very much helpful. Yeah, here we go. So this is a sloshing medium. So we have sloshing medium as well as we have the Westergaard's mass as well. So you can consider both those aspects in this software. We have one more question. How can we apply loading conditions factors for the loads? Yeah, that's an important question. So in this software, we have factor loads as well. So in the static analysis tab, we have an option called a loading combination load. So create a load set. So this is the load set. Let's say I'm going to consider load combination 2, LC2, let's say. I will select self weight, and let's say it is as 1.2. And I will select hydrostatic pressure. Let's say it is 1. I will select tailwater pressure, maybe 1, but maybe let's say the uplift pressure, maybe around 1.2 again. And then I will press OK. So here in the analysis works tree, you can find the LC2 load combination getting applied. So what I will do is I will go to the loading tab and only activate LC2 rather than activating all the loads, only activate LC2, which is the load combination set that I had created. There is some issue here because in the initial state, I had defined already sulfide. Now in this LC2 combination, I defined extra sulfide, right? So what I can do is I can simply go to this LC2, delete this option, delete the sulfide, and then press OK. And for the same sulfide, I can modify this from 1 to 1.2. So yes, we can actually apply the factors directly in the load, or we can simply apply the load combination that we had created in this software. So we can do both options in this case. So we can go for combinations via factor and then apply it in the analysis as well. Nice. Any more questions? Okay, great. That's all from my end. If you have any more questions, write it on the chat tab. We will get back to you as soon as possible.
You can also send us email. Our email is au@support@midas.com. And this session is recorded, so we will be posting on our YouTube channel. And after this session, we'll send you the link through your email. And then if you have any feedback, you can also contact us and let us know. Thank you so much, Harsha, and thank you everyone for joining today.
Thank you all. Thank you all for attending. Have a great day.
Harsha, there's another question.
One more question. Yeah.
Yes.
So can we calculate factor of safety against overturning? Yes. In this software, you will be able to get the normal force as you already had seen it in the interface stresses. But now instead of not just normal force, we can actually calculate the normal force centroid and the lever arm. So we have the resisting force. Sorry, that's the that's the resisting force. And let's say, and now we have the force applied onto the dam, right? So we can actually get the applied force at each and every node of the dam, and centroid multiplied by lever arm. As yes, we can get the applied forces as well as normal forces at the interface, and we need to export that to Excel sheet and then calculate the lever arm distances, and then we will be able to calculate overturning factor of safety as well. Yes, it is possible just by extracting the results and thereby doing some calculations on Excel sheet. Can we see stresses due to pore pressure in the dam body? Yes, we can actually get the pore pressure stresses in the model. In this particular analysis, which I had shown you, it is for non-porous material. Hence, you couldn't find the pore stress results in this software. But if you run a porous material and analysis for the porous material, yes, you will be able to see pore stresses in the foundation as well as pore stresses in the dam. Yes, you will be able to see both. Nice. Yes, thank you. Thanks again for attending this session. I hope you got a great time.
Right. Thank you,
We are
Harsha.
signing off.
Yeah.
Thank you, Eng.
Right.